All right, hello everybody. I'd like to make a little crash course video for the concepts in chapter 4 in case it's easier for you to learn via a lecture. Sometimes reading the textbook is hard and understanding all the concepts, so I thought I would review the concepts in chapter 4 and do a couple of practice problems with you that should help you with your homework. Chapter 4 is focused on Newton's laws and explaining motion. Okay, so I'd like to discuss with you today Newton's 3 laws of motion, some of the different types of forces that you see very commonly in everyday life, and applications. So we're going to solve some problems using Newton's laws. So far in this course, we've talked about describing motion only. We've talked about using kinematics to describe the velocity of an object, its acceleration, how far it has moved, and we've applied that to free fall and projectile motion. But we haven't yet discussed why does the object move that way in the first place. So in order to do that, we need to think about a force which causes an object to accelerate, which causes an object to change in its velocity, and causes an object to move and have a certain displacement. So I'm going to share my screen. What we're going to go over first is Newton's 3 laws of motion, which will help us understand what causes motion to occur in the first place. Let me share my screen. I'm going to bring up my whiteboard. Whoops. So Newton has 3 laws of motion. What's going on? Okay. His first law states that an object remains at rest or in uniform motion in a straight line unless it is compelled to change by an externally imposed force. You may have heard this one before. An object in motion stays in motion and an object at rest stays at rest. It's another way to say Newton's first law. So an object remains at rest or in uniform motion in a straight line. Unless it is acted on by an externally imposed force. Object at rest stays at rest, or an object in motion stays in motion, unless acted on by an outside force. That's exactly what the first law states. So what does this mean, really? This means if there is no net force on an object, so that if there's no net force, If you sum all the total forces acting on the object and they add up to 0, so no total force on an object means that the object is not accelerating. If the object is not accelerating, that can mean two things possibly. Either the object is completely at rest, stationary, or the object is moving in a straight line with a constant speed. Or what does that mean? Constant velocity in a straight line. Don't mind my cat in the background. Okay. So if an object is at rest, that means there's no net force on the object. If the object is moving at a constant velocity in a straight line, the object has no total force acting on it. So just because an object is moving doesn't necessarily mean it has a net force acting on it. If the object is moving in a straight line at a constant velocity, that means there's no net force acting on the object. Okay? If you're out in space, right, and you throw a wrench, the wrench is going to continue moving in a straight line at a constant velocity until it's acted on by an externally imposed force. So maybe it runs into another planet or another sun and it gets affected by that sun's gravitational field. Then it will begin to have an acceleration. But until that point occurs, it's going to move at a constant velocity in a straight line. If I'm dragging something across the floor, for example, okay, there's two forces, well, there's several forces acting on the object, but the two objects that are horizontally are my pull, the force of my pull in one direction and the force of friction in the other direction opposing the motion. If those two forces are equal in size and opposite in magnitude, equal in size and opposite in direction, the total force on the object is 0 in the horizontal direction, and the object is not going to accelerate. It may be moving at a constant velocity in a straight line, but it's not accelerating. Now, to get the box to move in the first place, I have to apply a force that's greater than the force of friction, and that gets it to accelerate and start to move. But once I get it moving and I apply a force that's equal to the force of friction on the box is just going to keep moving at a constant speed in a straight line. Now, in the first 3 chapters of the book, we discussed nothing about the object's mass, right? None of the kinematics equations have anything to do with mass. But we know that if I apply a force on an object, if I want to get it to accelerate, it depends on how massive the object is, right? So mass has to come into play somewhere here, and that's what Newton's second law says. Newton's second law is the same, basically it's saying the same thing as the first law, but it's saying it in a mathematical way. Newton's second law says that the acceleration of an object, if I get the object to accelerate, it's proportional to the net force that acts on the object divided by the object's mass, little m for mass. Remember, acceleration and forces are vectors. So if I have a net force to the right, that means that the acceleration is also going to point to the right. And the acceleration is inversely proportional to the mass. So the larger the mass under the same net force, the smaller the acceleration, right? That makes sense. If I apply a force on a really, really big boulder, its mass is huge, it's going to have basically zero acceleration. If I apply the same net force to a small ball, for example, it's going to accelerate a lot more. And this is in line with his first law of motion. If the net force on an object is zero, that means the acceleration on the object must be zero. And if the acceleration of the object is zero, it's either at rest or moving at constant velocity in a straight line. Oftentimes we see this equation rewritten like this: F net equals ma. The sum of the forces acting on the object is equal to the object's mass times its acceleration. We will use this one a lot when we actually get to applying Newton's law to solving problems. Newton's third law tells us about where does the force come from in the first place. In order for there to be a force, there has to be an interaction between two objects. If I have two objects, so object A, let's suppose object A exerts a force on object B. That means that object B exerts an equal and opposite force on object A. You may have heard it this way: for every action, there is an equal and opposite reaction. Okay, this is like action-reaction. This third law is a little bit tricky. Okay, it sounds simple, but sometimes it's a little bit tricky. Okay, the two forces in an action-reaction force pair always act on different objects. So for example, I push my hand up against the wall. My hand exerts a force on the wall. That's one force acting on the wall. The wall exerts a force on my hand in same size. Okay, but that force is acting on my hand. So the two forces are acting on different things, the wall and my hand. They're equal in size and opposite in direction. So I use this example a lot when I teach in person as well. Here's your windshield, and let's suppose there's a little bug flying along, and it hits your windshield. We know what happens to the bug, right? Let's think about the forces that are at play here. The windshield exerts a force on the bug. Let's suppose I was moving this way, right? The windshield is going to exert a force on the bug to the left. This is the force of the windshield acting on the bug. The bug also exerts a force on the windshield, right? And that force is equal in size and opposite in direction of the force that the windshield exerts on the bug. This is the force that the bug exerts on the windshield. Equal size force, opposite directions. Well, why does the bug splatter? I mean, what's the difference here? The forces are the same, size of the force are the same, their directions are opposite, but the size of the force is the same. The force of the windshield acting on the bug is the same as the force of the bug acting on the windshield. If I apply Newton's second law to this situation, if I think about the force that's acting on the bug, that should be equal to the mass of the bug times the bug's acceleration. Well, the bug's mass is very small, so I'm going to put a little m here on this side. The windshield, or basically the car, right, has a very large mass. So I'm going to put a really big M over on this side, mass of the windshield. These two things have to be this equal, right? They're the same size. So what does that tell us about the acceleration of the bug versus the windshield? Well, the acceleration of the bug is huge. And the acceleration of the windshield is very small. The car barely changes in velocity, right? The car doesn't change in its velocity at all when it hits a bug. So its acceleration it doesn't change in its velocity, so acceleration is basically zero or almost zero. The bug, however, undergoes a huge acceleration. It's flying along this way, its velocity is initially this way. The car hits it, it goes the other way now. It undergoes a huge change in its velocity. That means it has a very huge acceleration. It may be a negative acceleration because it completely goes the other way, right? But it's still a huge acceleration. That's the difference, right? A lot of the time we think, how can the forces be the same when the bug gets smashed? Well, the bug gets smashed because it undergoes a huge acceleration and its body just simply can't handle it. So those are Newton's laws of motion. Let's now talk about the different types of forces, and let's talk a little bit more about mass and its relationship to force. Let's talk about friction force. We can talk about normal force. Okay, let me clear. So let's talk about the different types of forces. There's actually four fundamental forces. I just want to go over this with you just so you know. Okay, there's four fundamental forces. And all other forces that we talk about are a result of these four fundamental forces. There's the gravitational force, so the gravitational force that pulls us towards the Earth, the gravitational force that acts between the sun and the Earth, or the Earth and the moon. Okay. Gravitational force is one of the four fundamental forces. Electromagnetic force is another fundamental force. And we will talk about this in future chapters. The force between two electrons, two protons, or the force on a moving charge within a magnetic field contribute to the electromagnetic force. And then there's two more forces that occur within the atom. Strong nuclear force. This has to do with the forces that keep all of those protons in the center of the atom together, and the weak nuclear force. The weak nuclear force has to do with the decay of certain atoms. Okay, we won't get into that much in this course. The two that we will talk about the most in this course is the gravitational force and the electromagnetic force. And all of the other forces that we will talk about in this semester are a result of these two forces. The gravitational force, we said it could be between the sun and the earth and the moon, ourselves and the earth. If I'm close to the surface of the earth, gravitational force, I'll write that capital F with the subscript G to indicate that this is the gravitational force, is equal to an object's mass multiplied by the acceleration due to gravity, G. As I get further away from the surface of the Earth, this changes and this force gets smaller, but for our course, when we're close to the surface of the Earth, the gravitational force is equal to the object's mass times the acceleration due to gravity, G. Another way to name the gravitational force, it's the same thing as an object's weight. So weight, when you talk about something's weight, you're actually describing how much force is on that object due to the Earth's gravitation. Okay. In the book, they call the force of gravity acting on the object equal to W. It's the same thing. So weight is a force. It has units of force would be newtons. Mass, M, is a scalar quantity, and it's a unit, it's a measure of an object's inertia. How easy it is to get the object moving, and how difficult is it for it to get the object to stop moving. The standard units for mass is a kilogram. And the direction of this gravitational force always pulls us down towards the Earth. So that's one type of force that we will talk about a lot in this chapter. Another force, so this is the result of the fundamental gravitational force. Okay. Another common force that we will talk about in this chapter is called the normal force. Now, in physics, normal doesn't mean like regular. It means perpendicular. So this force always points perpendicular to the surface. And so it's the force that points perpendicular to surface. So best example, if I have a table and I place a book on this table, there's a couple of forces acting on this book, right? We've already said there's the force of gravity acting on the book that acts directly at the center of gravity and points straight down. That's also known as the object's weight. We know that the object is not accelerating though, so there must be another force acting on this book to keep it at rest, and that force is the normal force, perpendicular to the surface of the book, so that between the table and the book, there's a force. The table exerts a force on the book upward. That force is what we call the normal force. It's perpendicular to the surface. I will call that Fn. It's a force. It's normal to the surface. In the book, they also denote it with a capital N. And it's perpendicular. So there's a right angle here between the table and the book. So the sum of these two forces, one of them points up, that would be a positive force. The other one points down, that would be a negative force. If the book is not accelerating up or down and it's at rest, the normal force must be equal to the object's weight on a flat surface. Now, I don't want you to think that the normal force is always directly upward, though. If the book is, for example, on a ramp, the force of gravity still pulls us directly down, but the normal force here is not straight up, rather it's normal to the surface, so it's going to point this way. So in this case, the object could start to have an acceleration down because the normal force does not completely counteract the object's weight. The normal force is actually a macroscopic effect of the electromagnetic force. The electrons in the table experience a repulsive force to the electrons in the book, and ultimately the book just doesn't go through the table because of that. Another force that you might see common in this chapter is the friction force. The friction force often opposes the motion. So if I'm dragging a crate across the floor, I'm pulling it one way, the friction force is going to oppose that motion and point the other way. Other common types of forces you might take advantage of in everyday life are things like tension forces, which are forces in like ropes or cables that allow you to transmit the force from your hand to the crate that you're pulling. There's also things like air resistance. Air resistance is a type of friction force. As the object falls through the air there's friction, right, between the air and the object. So air resistance is a type of frictional force we'll talk about in a little bit. Going back to the weight and mass and force of gravity, mass is an intrinsic property of the object. So if I know the object's density and I know how the volume of the object, I can determine the object's mass. And mass does not change. Mass remains constant. Whether I'm on the Earth, whether I'm on the moon, whether I'm on Mars, whether I'm floating out in outer space somewhere, my mass is always the same. It's an intrinsic property. It's a measure of the object's inertia. However, an object's weight may change. My weight on the Earth is different than my weight on the moon because the moon has a different gravitational acceleration. My weight is different in outer space. I'm almost weightless in outer space. My weight is different on Mars. Okay, so weight does change. depending on where I'm at. And as we said, the common units for weight in this chapter, we will use newtons, but another unit for weight is pounds, lbs. So when you read off that you're 150 pounds, you're actually describing your weight, not your mass. Of course, you can always calculate your mass from that. We can use a conversion factor that's given in the beginning of the book. But I want you to remember that weight and mass, even though in everyday life we use those terms interchangeably, in physics they have very specific meanings. So those are the different types of forces that we will most commonly see right now in this chapter. We will talk about the electromagnetic force in future chapters, so stay tuned for that. Let me clear on my drawing. So let's do a few examples just to help you, get a feel for how to apply Newton's laws to solving problems. So let's, for example, let's suppose we have a block. It has a mass of 5 kilograms. And let's suppose it's being pulled across the floor with a force of 10 newtons to the right. But there's a force of friction between the block and the floor of 2 newtons. So that force of friction has to oppose the motion. So if I'm pulling it this way, the force of friction's got to point that way to the left. And let's suppose it's 2 newtons to the left. What's the acceleration of the block? Let's apply Newton's second law here. I write N2L to say it's Newton's second law. So F net equals MA. The total force acting on the block equals mass times the object's acceleration. Okay. Let's only look at the forces that are moving in the horizontal direction. I want to solve for the object's acceleration, so let me solve for the acceleration. The net force, I've got 10 newtons pulling it to the right. Let's call that the positive direction. 2 newtons opposing that to the left. Let's call that the negative direction. Remember, forces are vectors, so we have to take into account their direction, and their direction is usually shown by sign. So I have 10 newtons to the right, that's positive. And then I have to subtract off the 2 newtons on the left. This is the net force. There's 8 newtons total acting on this object to the right. Dividing that by the object's mass, which is 5 kilograms. If I solve for the object's acceleration, it's 1.6. And remember our units for acceleration, it's a meter per second every second. Meter per second squared. The acceleration is positive, so that means it must be accelerating to the right. Now that I know the acceleration of the object, I could use kinematics equation to describe the motion, okay? So I can use kinematics to then describe the motion of the object. I could find final velocity, I could find how far it moves. If I could solve possibly for t, if I want to know if it moves 10 meters, right, how long does that take to occur? Things like that. So Newton's law tells us, why does this acceleration happen in the first place? It's because there's a net force acting on this block. Then once I know the acceleration, I can describe the object's motion. Let's do another one, except now let's think about it vertically, right? So let's suppose I have a ball I don't know, it's being pulled up by a string, and the tension in the string is, I don't know, let's say 5 Newton. Let's go with 15 newtons. Let's say the mass of this ball is 1 kilogram. And we want to know if I'm pulling it up with a force of 15 newtons, what is the acceleration here? Well, I'm applying a force upward on the object with a force of 15 newtons. But remember, what's the other force acting on this object? The force of gravity acting down, or the same thing as the object's weight, which is equal to mg. The acceleration is equal to the net force divided by the mass of the object. Let's solve for the net force first and then solve for the acceleration. F net equals, let's call going up, let's make it easy on ourselves, up is positive. Going downward is negative. So I have an upward force of 15 newtons, that's positive. I have to subtract off the weight of the object. So the weight of the object is its mass, which is 1 kilogram, times the acceleration due to gravity. I'll just use 10 here. It's 9.8 meters per second squared. If you want to use that, you can. Well, the book uses 9.8, so I'll just stick with 9.8 meters per second squared. So the weight of this 1 kilogram ball is 9.8, and it's a force. Remember, weight is a force, so its units are newtons. The weight is downward. It's a force acting downward, so I have to put a subtraction here, 9.8 newtons. Downward, so if I solve for that, I don't do mental math, sorry, 5.2 newtons is the total net force in the vertical direction here. So the acceleration is 5.2 newtons divided by the object's mass, 1 kilogram. The acceleration here is 5.2 meters per second squared. It's positive acceleration. That means it's being accelerated upward. This ball is not in free fall, right? There's a force acting on the ball. It's the force of my hand acting on it upward. If it was in free fall, the only acceleration that it would be feeling is the acceleration due to gravity. Let's do a little bit more practice with differentiating between weight and mass. So let's suppose I have a woman has a mass of 50 kilograms. Let's just say a person. Let's go with a person. A person's mass is 50 kilograms. That's their mass. It's in kilograms. What is the person's weight? In newtons and in pounds. Well, in newtons, I can simply use the object of the person's mass multiplied by the acceleration due to gravity. So the weight is equal to mg. Their mass is 50 kilograms. The acceleration due to gravity is 9.8 meters per second squared. That means that their weight is 490 newtons. that doesn't really mean much to us. We don't really know what a Newton is. But if you take a look at the front of your book, in the front cover, oops, here's my phone. The front cover has the conversion factor between newtons and pounds on Earth. So 1 Newton is equal to 0.2248 pound. So a Newton of force is about a quarter of a pound. So think about when you go to the deli, quarter pound of ham. That's 1 Newton, not very much. So if I wanted to know what her weight is in pounds, all I need to do is use the conversion factor between newtons and pounds. Conversion, I start with what I'm given, it's 490 newtons. Then I multiply by the conversion factor. 1 Newton on the bottom, so the Newton units cancel. 0.2248 pounds on the top. $110. So that is more a reasonable measure of weight for us. We're used to dealing with pounds. Her mass never changes, right? Whether she stays on the surface of the Earth, whether she goes to the moon, whether she's up in a rocket ship, doesn't matter. Okay, her mass always remains the same. What does change is her weight, because weight is the influence of gravity acting on you. Let's just do a couple more applications. So I'm sure that all of us have ridden in an elevator at least once in our life, right? So what would happen if you took a scale into the elevator, a bathroom scale, to measure your weight? Don't mind my stick figure. Have you ever experienced the feeling? So let's say you're on the bottom floor of the building, okay, and you push the up button, and the elevator starts to move upward. And that means it's accelerating because it has 0 velocity, and then after a certain amount of time, it has a constant velocity. But during that period, while it's changing its velocity upward, it's accelerating upward. And during that time where the elevator is accelerating upward, have you ever gotten the feeling of yourself being a little bit heavier, getting that heavy feeling in your stomach? And then when you get to the top of the building and the elevator slows down, what happens there? The elevator decelerates, and you kind of get that funny, like butterfly light feeling in your stomach, right? What's actually happening is that the normal force that's acting on you from the elevator floor is changing when the elevator is accelerating up or decelerating when it reaches the top. So let's suppose the elevator is accelerating up. Okay, so this is like you're starting on the bottom floor and you're working your way up. While the elevator is accelerating up, let's think about what the scale will read. There's two forces on you. So let's analyze the forces that are on you, and then we can identify what the scale reads. So there's the normal force of the scale acting on your feet, right? And it points directly upward, normal to the surface. So that's one of the forces acting on you. The other force is the force of gravity acting on you, pointing down. So there's two forces at play here. The normal force points up. Let's make that direction positive. Then the gravitational force is down. That's the net force. That has to be equal to the object's mass, which is your mass, times your acceleration. Your acceleration is positive. So this side is positive up. The scale exerts a normal force on you upward. You exert an equal and opposite force on the scale. And that's what the scale reads. Okay? So if I can solve for the normal force here, that's going to tell me what the scale reads because that's the same magnitude that you exert on the scale. So the normal force, and I'm going to write the force of gravity equal to mg. That's your weight. So the normal force when you're accelerating upward in the elevator is actually greater than your weight. The normal force has to take into account your weight plus the fact that the elevator is accelerating upward. So the normal force is larger than your weight and you feel heavier. And the scale would actually read heavier. Now, once the elevator gets to a point where it's moving upward, but it's no longer accelerating, the scale will go back to its normal reading. So if you're 140 pounds, the scale will go back to 140. And let's say you then get to the top. The elevator starts to decelerate, so the acceleration is now pointing down. Two forces on you are still the normal force, which is up, and your weight, which is down. But now the elevator is slowing down in the upward direction, so its acceleration is downward. So this right-hand side has to be negative ma because the acceleration is down. So solving for the normal force now, it's Fg minus ma. So when you get to the top and the elevator starts to slow down, the scale will actually read something lighter than your weight because it's mg minus ma. So when you're accelerating upward, you feel heavier. And when you have an acceleration downward, kind of like when you're slowing up, getting to the top of the building, you feel lighter. And the scale would read something lighter. Now, when you come to a complete stop, when you reach your floor and you're no longer accelerating, the scale will go back to its normal reading. You have also experienced this if you've gone on a roller coaster ride. When you get to the bottom of the hill, you feel that heavier feeling because at the bottom, you're accelerating up, actually. And at the top of the hill, you get that lighter feeling in your stomach. Your acceleration vector at the top of the hill actually points down and you feel lighter at the top of the hill. Last type of force I'd like to talk about conceptually is the force of air resistance. We've ignored air resistance in the last few chapters, but I just want to conceptually help you understand what air resistance is and why does it seem to affect certain objects more than others. So let's compare two things, very extreme things. Let's suppose this is a huge elephant, and let's suppose this is a tiny feather. Elephant has huge mass, feather has very small mass. And let's suppose we drop these two from a high building. Not a good idea, obviously, but hypothetically. We know that they're both going to have the force of gravity acting on them. So they're both going to have the force of gravity acting downward on them, which is equal to their weight. And that's equal to mass times the acceleration due to gravity. I'll make this a big M since this is for the elephant. So the elephant obviously has a lot more weight than the feather. But there's another force at play here, which is the force of air resistance. And for our sake, let's assume that the force of air resistance points opposite the motion of the object, so the air resistance is going to point upward. And I'll denote that with a capital R for resistance. It's a force. And just to let you know, the air resistance is proportional to, as you would imagine, the surface area of the object and the object's velocity. And C refers to a few different other things, such as the fluid that you're actually moving through. So it could be air, could be water, could be oil, whatever it is. We don't need to worry about that very much. Resistance makes sense that it would depend upon the surface area of the object and its velocity. Faster the object is moving, the more air molecules that it's hitting, the more resistance it's going to feel. When I first drop these things from the tall building, there is not any air resistance acting on them yet. But as they start to fall, they're going to experience more and more air resistance as they pick up speed. The elephant obviously has more air resistance than the feather because of its larger surface area. But the elephant also has a lot more weight than the feather. So if I look at the net force acting on each of these items, I've got the air resistance pointing up, the weight acting downward, and that should be equal to the object's mass times its acceleration. The feather, as it drops, its weight is very small. It also has a small air resistance compared to the elephant, but what happens is that eventually, as this thing drops, R, the air resistance, can become equal to the weight. Because the weight of this feather is so small and the air resistance is rather small. It doesn't take very long for the air resistance acting on this feather to be equal to the weight of the feather. So this feather is only going to accelerate for a short time because once the air resistance becomes equal to the weight, the acceleration is zero. It's no longer accelerating downward, and we would say that it has reached terminal velocity. The feather's terminal velocity is very low because this thing doesn't accelerate very much. I drop it, the air resistance quickly becomes equal to the object's weight. It no longer accelerates and it reaches terminal velocity very quickly. So since this thing doesn't accelerate very much, it reaches terminal velocity very quickly and then just kind of floats to the ground at that terminal velocity, which is very small. On the other hand, the elephant, it has a huge amount of weight, so it's going to take a huge amount of air resistance to actually overcome that weight. So that means that the elephant is going to accelerate for a lot longer than the feather. Takes a long time for R to become equal to the elephant's weight. So it accelerates for a long time before reaching terminal velocity. So this thing is going to accelerate a long time. It's going to get a very, and if it ever does reach terminal velocity before it hits the ground, it's going to take a long time for that to happen. And that terminal velocity is going to be very large. So the elephant accelerates for a longer amount of time than the feather. It has a larger terminal velocity than the feather, and that's why the elephant is going to hit the ground first. I just wanted to let you know about air resistance. I don't want you to think that we've completely ignored it, but it's not easy to take it into account because we have to take into account the fluids that we're in, the shape of the object, and how fast the object is moving. But conceptually, this is why we see differences between like feather falling versus an elephant versus a brick. But if air resistance was negligible, the elephant and the feather would hit the ground at the same time. All right, so I hope that you enjoyed this quick crash course on forces. I hope this helps you with some of your homework problems. If you have questions or concerns, feel free to email me, and I'll post another video next week on energy. I'll talk to you soon. Bye.